Hi, my name is Davide Breoni and I'm an ITN researcher. Today I will talk to you about my research. So, what I work with is the short-time behavior of active matter in a disordered potential landscape. And what it means I will explain briefly. So, imagine a system with only one particle in a two-dimensional space. This particle has to be active, which means that it has an engine which moves it around, and the system is overdamped, meaning that the viscosity is so large that the particle basically has no inertia. The really interesting thing, though, that I consider is that this particle moves in a random landscape. So we don't know prior to its realization how it is actually made. Now, given this hypothesis, this will be the equations of motions. I won't bore you with the details. What you just need to know is that the motility and potential random fields appear in this equation as the delta V term for motility and the gradient of big V for the potential. And these two fields are random in the form which is described in the lower part of this slide. So they are an infinite sum of modes, cosines and sines with Gaussian prefactors, in our case called epsilon. Now, the procedure to calculate the MSD can be easily, MSD meaning a mean square displacement of the particle, can be easily explained. We just Taylor approximate the fields because otherwise, of course, it's impossible to do any analytical calculation. So we Taylor expand around the initial position, R0. We solve the system, calculate the short time expansion of this mean square displacement, and of course remember that the higher order term don't disappear in the short time expansion just because we ignore them, so we have to kick them back in with perturbation theory. And finally, if we want to actually compare our result with experiment or simulation, what we have to do is average over the initial position R0, which basically gives us an average over the noise in space of these motility and potential fields. So we also implemented a simulation, and you can see how, well, in this case, the red line, which represents the simulation result for the mean square displacement, goes very close to the green line, which instead is our theory, especially for short times, but that's exactly what we are interested into. Now, where are we going next? So the obvious procedure would be to just take more complex system and do the same thing, and that's what we're planning to do. First with an underdamped Ornstein-Uhlenbeck system, so meaning that it has inertia because underdamped, and Ornstein-Uhlenbeck means that there is no white noise, but we have instead colored noise. And afterwards we want to go with active particle in viscoelastic fluids. So fluid with let's say memory term, which makes things, of course, more difficult. So yeah, this is my presentation. Thanks for watching.